Tonight, we're going to watch our sun die. Not as a distant scientific abstraction, not as a number buried in an astrophysics textbook, not as a theoretical event so far removed from human experience that it fails to touch you. We're going to watch it die the way you'd watch anything important die. With attention, with honesty, with the full weight of what it means. We're going to follow the sun through every stage of its death. From the slow, invisible brightening already underway right now, to the evaporation of Earth's oceans, to the violent expansion that will swallow the inner planets, to the helium flash, to the second expansion, to the shedding of the outer layers, to the brief, glowing planetary nebula, to the white dwarf cooling in silence across billions of years. We're going to see it all. And by the end of tonight, you're going to understand not just how the sun dies, but what that death means for Earth, for life, for us, for whatever we might become if we're still here or somewhere else when the end arrives. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something most people take completely for granted. The sun is burning right now. At this exact moment, as you watch this, the sun is converting approximately 600 million tons of hydrogen into helium every single second. Not per minute, not per hour, every second. The energy released by that conversion, a tiny fraction of the mass being transformed directly into energy, according to Einstein's equation E equals mc squared, travels outward from the core of the sun through radiation and convection, eventually reaching the surface, and then crossing 150 million kilometers of vacuum in 8 minutes to reach your skin as warmth. That process has been running without interruption for approximately 4.6 billion years, before the first fish existed, before the first plant existed, before the first single-celled organism learned to harvest sunlight, before the Earth itself had fully solidified from the cloud of gas and dust from which it formed. The sun was already burning, already converting hydrogen to helium, already filling the inner solar system with light and warmth. And it cannot go on forever. The sun is not infinite. It has a fuel supply. That fuel is massive, almost incomprehensibly massive. But it is finite, and we can calculate with genuine precision how much is left, how fast it's being consumed, and how much time remains before the fire changes. The sun contains approximately 2 times 10 to the 30th kilograms of total mass. That is a 2 followed by 30 zeros. Of that total mass, roughly 70% is hydrogen and about 28% is helium, with the remaining 2% being heavier elements. But not all of that hydrogen is available for fusion. Nuclear fusion requires extraordinarily high temperatures and pressures, temperatures of roughly 15 million degrees Celsius, and pressures millions of times greater than Earth's atmospheric pressure. Only the core of the sun reaches those conditions. The core makes up approximately the inner 25% of the sun's radius, which translates to roughly 10% of the sun's total volume, which means roughly 10% of the sun's hydrogen is in the fusible zone. That sounds like a small fraction. But 10% of the sun's hydrogen is still an almost incomprehensible quantity of fuel. Stars like our Sun, known as G-type main sequence stars, ordinary yellow dwarfs, have total main sequence lifetimes of approximately 10 billion years. We are currently 4.6 billion years in. We are almost exactly in the middle of the Sun's life. Think about what that means. The Sun is middle-aged. It has been burning for longer than the Earth has existed, longer than life has existed, longer than any geological feature you can name has persisted. And it still has approximately 5 billion years left before it leaves the main sequence. 5 billion years of continued hydrogen fusion in the core. 5 billion more years of warmth and light and the energy that drives every process on this planet. That sounds reassuring. It sounds like an eternity. But here is what most people don't know, and what changes everything. The Sun is already changing, right now, measurably, irreversibly. As the Sun fuses hydrogen into helium, the composition of the core gradually shifts. Helium nuclei, the product of fusion, are heavier and more compact than the hydrogen nuclei from which they're made. As helium accumulates in the core becomes denser. Gravity pulls the denser core inward slightly. That inward contraction raises the temperature and pressure. Higher temperature and pressure increases the rate of fusion. A faster fusion rate releases more energy. More energy means a more luminous Sun. The Sun is brightening. Slowly, steadily, relentlessly. Over the 4.6 billion years it has been alive, the Sun has increased its luminosity by approximately 30%. 4 billion years ago, the Sun shone with roughly 70% of its current brightness, and it will continue brightening for as long as it remains on the main sequence. By the time the Sun is 5 billion years older, when it's preparing to leave the main sequence, it will be approximately 67% more luminous than it is today. That gradual brightening is not academic. It has direct, measurable, catastrophic consequences for life on Earth. And it begins much sooner than most people realize. Most discussions of the Sun's death focus on the red giant phase, on the swelling Sun consuming the inner planets, on the dramatic, visible death of a star. And we will get there. But that's not the first thing the Sun's aging does to Earth. The first thing it does is far more subtle, and it begins in approximately 500 million to 1 billion years. Earth's climate is a system of extraordinary complexity and extraordinary sensitivity. The amount of solar energy arriving at the top of the atmosphere, a quantity called the solar constant, currently about 1,361 watts per square meter, drives everything. The temperature of the surface, the evaporation of water, the precipitation cycles, the growth of plants, the chemistry of the atmosphere, the distribution of ice and ocean. Everything responds to the total energy input from the Sun. Right now, that system is in a rough balance. Energy in equals energy out. The planet warms by day and cools by night. The greenhouse gases in the atmosphere, water vapor, carbon dioxide, methane, others, trap some of the outgoing infrared radiation, keeping the surface warmer than it would otherwise be. The reflectivity of clouds and ice and land surface bounces some incoming sunlight back into space before it can heat anything. The carbon silicate cycle, a geological process where carbon dioxide is removed from the atmosphere by chemical weathering of rocks and returned to the atmosphere by volcanic outgassing, regulates atmospheric carbon dioxide on timescales of millions to hundreds of millions of years. This system is stable, but it is not infinitely stable. It can be pushed past tipping points from which recovery is impossible. A 1% increase in solar luminosity sounds trivial, but climate models show that a 1% increase in solar output is enough to produce significant warming, enough to push the tropics toward greater aridity, enough to shift precipitation patterns globally. A 10% increase, which is roughly what we'll experience in about 1 billion years, is enough to trigger feedbacks from which the climate system cannot recover. Here is how it works. As the sun brightens, the oceans warm. Warmer oceans evaporate faster. Water vapor is itself a powerful greenhouse gas, more powerful than carbon dioxide molecule for molecule. So more water vapor in the atmosphere means more warming, which means more evaporation. The feedback accelerates. Models of this process, called the runaway greenhouse effect, suggest that once it begins in earnest, it cannot be stopped by any natural mechanism. As the oceans warm and evaporate, water vapor rises into the upper atmosphere. In the upper atmosphere, in the stratosphere and above, ultraviolet radiation from the sun hits water molecules and breaks them apart through a process called photolysis. The hydrogen atoms, being the lightest element in the universe, achieve escape velocity from Earth's gravity and are lost to space. The oxygen atoms combine with other atmospheric constituents or are consumed by surface reactions. This is not a fast process. It takes millions of years, but it is irreversible. Each water molecule destroyed in the upper atmosphere represents water that will never return to the ocean. The ocean level drops, slowly at first, then faster as the feedback intensifies. The deep oceans are enormous. They contain roughly 1.4 times 10 to the 21st power liters of water. And it takes time to evaporate and dissociate that quantity. But the sun has time. Within approximately 1 billion years, the most optimistic estimates push this to 1.5 billion years, the most pessimistic to 500 million years. The Earth's surface oceans will be gone. Not frozen, not hidden underground. Gone. The hydrogen lost to space. The oxygen largely bound into rocks and atmospheric chemistry. A planet that was once 70% covered in liquid water will be dry, completely dry, as dry as the surface of Venus is today. And Venus is not an accident. Venus is a warning. Venus and Earth are nearly identical in size, in mass, in composition, in their distance from the Sun relative to the total stellar output. They formed from the same disk of material. They should be nearly identical worlds. But they are not. Venus has a surface temperature of about 465 degrees Celsius, hotter than the surface of Mercury despite being farther from the Sun. Its atmosphere is 96% carbon dioxide, with crushing surface pressure about 90 times Earth's atmospheric pressure. Its clouds are sulfuric acid. Venus almost certainly had oceans once. Evidence suggests it may have had liquid water for up to 2 billion years. But the sun's early brightness, or some other factor, triggered a runaway greenhouse effect. The oceans evaporated. The hydrogen was lost to space. The carbon dioxide, which had been locked in carbonate rocks the way it is on Earth, was released into the atmosphere through volcanic outgassing without a water cycle to reabsorb it. The atmosphere collapsed into a dense blanket of carbon dioxide and the temperature skyrocketed. Venus is what Earth becomes, not immediately, not in 1 million years, not in 100 million years. But eventually, with certainty, Earth becomes Venus. The specific trigger will be the brightening sun pushing Earth's climate past the point of no return, initiating the runaway greenhouse, evaporating the oceans, dissociating the water, releasing the carbon. The timeline is approximately 1 billion years from now. Perhaps a bit more, perhaps a bit less, depending on how the climate system responds. But here is the more important number. Complex life on Earth almost certainly ends before the oceans are fully gone. Multicellular life, plants, animals, fungi, complex ecosystems requires more than just liquid water. It requires a stable temperature range. It requires sufficient carbon dioxide for photosynthesis, but not so much that the greenhouse is out of control. It requires an atmosphere with appropriate pressure and composition. As the sun brightens and the climate warms, all of these conditions begin to degrade long before the oceans fully evaporate. Current models suggest that the conditions suitable for complex life on Earth's surface will deteriorate to uninhabitable within approximately 500 to 800 million years. Call it 600 million as a rough midpoint. 600 million years is a long time, longer than complex animal life has existed on Earth. The Cambrian explosion, when most major animal body plans appeared, was 540 million years ago. Complex life as we know it has existed for roughly 600 million years. We have perhaps 600 million years left. We are not in the beginning or middle of the story of life on Earth. We are near the end of it. The second half, the final act, though it stretches hundreds of millions of years, and we are the only species in the history of this planet that knows it. Every trilobite that ever lived, every dinosaur that ever walked, every creature in every ocean and forest and desert for the past 600 million years, none of them knew. They lived and died and evolved and went extinct without any awareness of the star above them, of what it was, of what it would become, of how much time remained. They simply lived. We are different. We looked up. We measured. We calculated. And now we know. That knowledge is extraordinary, and it carries weight. Let's skip forward now, past the billion years of gradual warming, past the evaporation of the oceans, past the scorching of the surface and the loss of the atmosphere, past the period when Earth has become a hot, airless, dry rock in the inner solar system, recognizable as a planet, still orbiting the sun, but as alien and lifeless as anything you could imagine. We're now approximately 5 billion years in the future. Earth has been uninhabitable for roughly 4 billion years. The sun has been brightening slowly and steadily throughout this period, as it has throughout its entire life. And now, approximately 5 billion years from now, something fundamental changes. The hydrogen in the sun's core runs out, not depleted to a low level, not reduced to an inefficient trace, gone. The core hydrogen, the fuel that has powered the sun for 10 billion years, is exhausted. The proton-proton chain reaction that has been running continuously since before the Earth existed. The reaction that converts 4 hydrogen nuclei into 1 helium nucleus and releases energy, stops. When core hydrogen fusion ceases, the energy output from the core drops dramatically. For billions of years, this energy has been pressing outward, creating a radiation pressure that exactly balanced the inward pull of gravity. The sun has been in a precise equilibrium, gravity pulling in, radiation pushing out, for its entire main sequence life. That equilibrium is what makes the sun the stable, reliable star it has been. Without that outward energy, the equilibrium breaks. Gravity wins. The core begins to contract. What happens next is one of the most dramatic sequences in stellar physics, and it unfolds over hundreds of millions of years in a progression of events, each more extreme than the last. As the helium core contracts under its own gravity, it heats up. This is counterintuitive but fundamental. Compressing a gas raises its temperature. The contracting helium core gets hotter, much hotter. That heat radiates outward into the layer of hydrogen surrounding the core, the shell of hydrogen that had been sitting there for 10 billion years. Too far from the core to participate in fusion, simply along for the ride. When the temperature in this hydrogen shell reaches approximately 10 to 15 million degrees Celsius, the same threshold required for core fusion, something extraordinary happens. Shell hydrogen fusion ignites. A ring of hydrogen fusion surrounding the entire helium core begins burning. And because the shell surrounds the core, it has a much larger surface area than the core ever had. The energy production from shell fusion is enormous. Far more power than the core was producing at the end of its hydrogen-burning life. That enormous energy output has to go somewhere. Radiation pressure in the outer layers of the sun increases dramatically. The outer layers begin to expand. The sun starts to swell. This is the beginning of the transition from main sequence star to red giant. It doesn't happen overnight. It doesn't happen in a million years. The transition from main sequence to fully developed red giant takes hundreds of millions of years. But once it begins, it is irreversible. As the outer layers expand, the surface area of the sun increases. The same total energy is now spread over a larger surface, which means the surface temperature drops. A hotter, smaller surface glows blue-white or white. A cooler, larger surface glows orange or red. The sun's color shifts from the yellow-white we see today toward orange, then toward red. The sun is becoming a red giant. Let's pause here and think about what this looks like from outside the solar system. Any civilization in a nearby star system, perhaps orbiting Alpha Centauri or Barnard's star, that happen to be watching our sun through their telescopes over these hundreds of millions of years, would see it gradually changing, brightening, swelling, cooling in surface temperature but increasing in total luminosity. They'd recognize what was happening immediately. They've seen it before. Every sun-like star in the galaxy goes through this process. It's ordinary. It's expected. It's the fate of any star that starts life with roughly the sun's mass. For them, it's astronomy. For anything still alive in this solar system, if anything is, it's the apocalypse. The sun's expansion does not proceed smoothly and steadily. It accelerates. The rate of shell fusion increases as the core continues to contract and heat up, providing more energy to the burning shell. The outer layers expand faster and faster. The sun's radius grows from its current 696,000 kilometers towards something staggering. The sun will swell to approximately 200 times its current radius. 200 times. The current sun could fit inside the expanded red giant sun roughly 8 million times by volume. The red giant sun's outer envelope will extend to approximately 150 to 200 times Earth's current orbital distance from the sun, which puts its outer edge somewhere between the current orbits of Earth and Mars. But that calculation has a complication. As the sun expands into a red giant, it loses mass. Red giants are not contained objects. They are loosely bound assemblages of plasma, and their outer layers are continuously blown away by powerful stellar winds. Streams of particles ejecting from the surface at hundreds of kilometers per second. During the red giant phase, the sun will shed roughly 30% of its total mass through these stellar winds. Mass loss has a direct effect on orbital dynamics. The gravitational force between the sun and the planets depends on the sun's mass. If the sun loses mass, its gravitational grip weakens. The planets, responding to the reduced gravity, drift outward. Their orbits expand. Mercury, already the closest planet to the sun, will be consumed early in the red giant phase regardless. Venus will follow. What happens to Earth depends on a precise competition between two processes: how fast the sun's outer envelope expands and how fast Earth's orbit drifts outward as the sun loses mass. This is one of the most actively debated questions in late stellar evolution research. Different models give different answers depending on the assumed rates of mass loss, the timing of the expansion, and the orbital mechanics involved. Some models predict that Earth's orbit will expand just fast enough to stay ahead of the expanding solar envelope, barely escaping engulfment. Others predict that the expansion slightly outpaces the orbital drift, and Earth is consumed. The most recent detailed calculations lean toward engulfment. The Earth, in these models, is eventually overtaken by the sun's expanding atmosphere and spirals inward through the low-density outer layers of the red giant, losing orbital energy through drag until it either evaporates in the extreme heat or falls into the denser inner layers and is destroyed. But here is something important to understand. Whether or not the physical matter of Earth is literally consumed by the sun, the practical outcome is identical. Earth at this stage is not a planet in any meaningful sense. It has no atmosphere. It has no water. It has no surface that any chemistry we know of could operate on. The surface temperature is thousands of degrees. Rock is molten or vaporized. Any metals are liquid. The concept of a habitable surface is as meaningless here as it would be on the surface of a star. The Earth, the specific blue and white world with oceans and weather and life, ended approximately 4 billion years before this point. What the red giant sun is engulfing or approaching is a scorched, airless, metallic rock, a ruin, a remnant, not a planet in the sense that matters. The red giant phase represents the physical destruction of the remnant. The actual death of Earth happened billions of years earlier, quietly, through the simple mechanism of a brightening star warming a world past the point of recovery. Let's talk about what the red giant sun looks like from a distance. The sun, at maximum red giant size, would be an enormous object in the sky of any surviving planet. From Mars's current orbital distance, though Mars will have drifted outward substantially by this point, the sun would fill a significant fraction of the sky. Not the small disk we see from Earth today, appearing about half a degree across. An enormous, dim, red sphere, filling perhaps 40 or 50 degrees of the sky. Dimmer per unit area than the current sun, but so much larger that it still dominates everything. The color would be a deep, rich red-orange. The surface temperature of the red giant sun will be around 2,500 to 3,500 degrees Celsius, compared to the current 5,500 degrees. That cooler temperature shifts the peak emission from visible light toward infrared. The red giant would look red in a way the current sun doesn't. Genuinely, vividly red. Not the orange red of a sunset, which is an atmospheric effect, but intrinsically red light from a genuinely cool stellar surface. From the perspective of the outer planets, from Jupiter's new orbit, farther from the sun than it is today due to mass loss expansion, the sky would be dominated by this enormous red sphere. No blue sky, no atmosphere, just the vacuum of space and the overwhelming redness of a dying star filling a quarter of the visible sky. And yet, Jupiter would be warming. For the first time in 10 billion years, Jupiter's cloud tops would be experiencing significantly elevated temperatures. The eternal cold of the outer solar system would be retreating. The habitable zone, that band around the star where liquid water can exist on a planetary surface, would have migrated outward dramatically. We need to talk about what this means, because it is one of the strangest and most haunting implications of the sun's death. The habitable zone of a star is not a fixed location. It depends entirely on the star's luminosity. A dimmer star has a habitable zone closer in. A brighter star has one farther out. As the sun brightens through its main sequence life, and then dramatically increases its luminosity during the red giant phase, the habitable zone migrates outward. Right now, the habitable zone extends roughly from about 0.95 to 1.4 astronomical units from the sun, from just inside Earth's orbit to just outside it. Venus is too close. Mars is too far. Earth sits comfortably in the zone. As the sun enters the subgiant phase and begins brightening noticeably, perhaps a billion years from now, the habitable zone begins moving outward. Mars, currently just outside the zone, enters it. For a period of perhaps 100 to 200 million years, Mars might be warm enough for liquid water on its surface if it still had an atmosphere. It doesn't, having lost its atmosphere billions of years ago. But the principle holds. The zone moves. As the sun expands into a red giant and its luminosity increases by a factor of thousands, the habitable zone leaps outward dramatically. It reaches the asteroid belt. It reaches Jupiter. It reaches Saturn. In principle, for a period during the red giant phase, the outer solar system, which has been frozen since the solar system formed, could briefly experience conditions where liquid water could exist on the surfaces or in the subsurface environments of the moons of Jupiter and Saturn. Europa, Jupiter's ice-covered moon with a liquid ocean beneath, is kept warm today by tidal heating from Jupiter's gravity, not by the sun. As the sun's luminosity increases dramatically, Europa would receive far more solar energy. Its ice shell might thin, might melt. The subsurface ocean might become a surface ocean. For the first time in its existence, Europa might have open water at its surface, sunlit, potentially chemically active in new ways. Ganymede and Callisto, currently frozen worlds, might see their ice surfaces begin to melt. Titan, Saturn's moon with a thick nitrogen atmosphere and liquid methane lakes, would undergo a dramatic transformation as methane evaporates and the chemistry of the atmosphere changes under increased solar radiation. Enceladus, which vents water vapor from internal heating today, might see its ice crust melt entirely, becoming a small, warm ocean world briefly. This is perhaps the most poignant aspect of the entire story. As Earth is being destroyed, scorched, dried, eventually consumed or nearly consumed by the expanding sun, the outer solar system is experiencing its first warmth. Worlds that have been frozen since the solar system formed are briefly thawing. If life exists in any of these frozen moons today, in the subsurface oceans of Europa, Enceladus, or Titan, that life would experience an extraordinary event. The ice above them melting, sunlight penetrating into waters that have never seen it, new chemical energy sources becoming available, new chemistry becoming possible. Whether any of those worlds could sustain life through the transition is uncertain. The red giant phase is brief by astronomical standards, perhaps 100 million years at maximum, and the habitable zone sweeps through the outer solar system rather than pausing there indefinitely. As the sun continues to expand and its luminosity increases further, even the outer solar system becomes too hot. The habitable zone sweeps past and into the dark beyond the solar system. What might have been a brief bloom of habitability in the outer solar system ends. The outer moons are boiled. Their oceans vaporize. Their thin atmospheres are stripped away by the solar wind of the dying star. And then the sun begins to shed its outer layers entirely. If life existed in Europa's ocean today, it would experience several billion years of cold existence. Then a brief, perhaps 100 million year period of warmth and new possibility. Then destruction. That sequence of events, long cold stasis, brief warmth, final destruction, may be the most common pattern for life in solar systems around sun-like stars. Life arises in the cold subsurface, endures for billions of years, briefly sees its star's last warmth, and then is extinguished when that warmth becomes lethal. We don't know if any life exists in the outer solar system today. We have strong reasons to believe Europa has a liquid ocean, and liquid water plus chemical energy is the minimum requirement for life as we know it. We've found life in extreme environments on Earth that are far harsher than Europa's ocean is likely to be. We've found life in dark, cold, pressurized subsurface environments with no sunlight whatsoever, powered entirely by chemical energy from hydrothermal vents. If life exists in Europa's ocean, it has existed there for perhaps 4 billion years. It has existed in complete darkness, under a kilometers-thick ice shell, sustained by the gentle tidal heating from Jupiter's gravity. It has never known sunlight, never known warmth from the sun, never known anything beyond its cold, dark, chemically active ocean. And in approximately 5 billion years, its ice ceiling will begin to thin. Light will, for the first time, begin to penetrate. New chemistry will become available. And then, before it can adapt, before it can evolve to take advantage of this new energy source, the heat will become lethal and everything will end. It's a story so strange and so poignant that I can barely hold it in my mind. Life that never saw the sun, living for billions of years in the dark, briefly experiencing light, then gone. Let's return to the sun's core. Because while all of this is happening in the outer solar system, something even more dramatic is building inside the dying star. We left the sun with its helium core contracting, getting denser and hotter, while shell hydrogen fusion drives the enormous expansion of the outer layers. The helium core continues contracting. The temperature inside it climbs toward 100 million degrees Celsius. 100 million degrees. 6 times hotter than the current hydrogen-fusing core. At 100 million degrees, something new becomes possible. The helium nuclei in the core, the ash of hydrogen burning, the accumulated product of 10 billion years of fusion, become themselves a fuel. At 100 million degrees, helium nuclei can fuse with each other. Through a process called the triple alpha reaction, 3 helium nuclei, alpha particles, combine to form one carbon nucleus. With additional helium, carbon can fuse with another helium nucleus to form oxygen. The helium ignites. But the way it ignites, for a star like our Sun, is not gradual. It is not a gentle transition from helium inert to helium burning. For low-mass stars, the helium ignition is an explosion, an event called the helium flash. Here is why. During the contraction of the helium core, the material in the core reaches such high density that it enters a state called electron degeneracy. In a normal gas, pressure depends on temperature. Heat the gas and the pressure rises, which counteracts any compression and restores equilibrium. This is what keeps normal gas stars stable. But in electron-degenerate matter, pressure is almost independent of temperature. It's determined instead by quantum mechanical effects. Specifically, the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. In degenerate matter, you can pour heat into the gas. You can raise the temperature dramatically. And the pressure barely changes. The gas doesn't expand to relieve the pressure. It stays compressed. This creates a catastrophically unstable situation when fusion ignites. When helium fusion begins in the degenerate core, it releases enormous energy. That energy heats the core further. In a normal gas, higher temperature would mean higher pressure, which would mean the core expands and cools, throttling back the fusion rate, a negative feedback that keeps stars stable. But in degenerate matter, the temperature rises without a corresponding pressure increase. The core doesn't expand, so the fusion rate increases. More heat, more fusion, more heat. The temperature runaway proceeds unchecked. In a matter of seconds, perhaps as few as a few seconds, the helium flash releases approximately 10 to the 28th power watts of power. That is roughly 100 billion times the luminosity of the entire current Sun. For those few seconds, the energy output of the Sun's core equals the combined energy output of roughly 100 billion suns. You would not see this. This is one of the most counterintuitive facts about the helium flash. Despite releasing more energy than 100 billion suns in those few seconds, the helium flash produces no visible brightening at the surface of the star. The energy is absorbed and redistributed through the enormous outer layers of the red giant before it ever reaches the surface. What you'd see, watching from outside, is essentially nothing unusual during the flash itself. The change becomes apparent only over hundreds of thousands of years as the star's structure reorganizes. What the helium flash actually does is lift the core out of degeneracy. The enormous energy released heats the helium until it's no longer degenerate, until it behaves like a normal gas again. And at that point, the runaway stops. The negative feedback that normal gas provides kicks in. The core expands slightly. The temperature drops slightly. The fusion rate stabilizes. The helium flash ends. And the Sun enters a new phase of its life called the horizontal branch. or for Sun-like stars, the helium main sequence. For approximately 100 million years, the Sun stably fuses helium in its core and hydrogen in the surrounding shell. It's more luminous than the current Sun, but less luminous than the maximum red giant phase. It's somewhat smaller than the maximum red giant. This phase is brief, 100 million years compared to the 10 billion years of hydrogen main sequence burning. The difference in timescales reflects the difference in energy yield. Helium fusion is less efficient than hydrogen fusion. Less energy per unit mass is released. The fuel runs out faster, and when the helium in the core is exhausted. When the core is now composed primarily of carbon and oxygen, the products of helium burning, the whole sequence repeats. The end of core helium fusion triggers a second phase of stellar death that mirrors the first, but exceeds it in almost every way. The carbon-oxygen core contracts under gravity, heating up. The contracting core heats the surrounding shell of helium to fusion temperatures. Shell helium fusion ignites. The energy output increases dramatically. The outer layers expand again. The Sun enters what astronomers call the asymptotic giant branch, or AGB phase. This second red giant phase is more extreme than the first. The Sun swells even larger. Its luminosity climbs even higher. It pulsates, not with a rapid heartbeat, but with long, powerful oscillations driven by the competing forces of fusion energy and gravity. The star breathes over periods of thousands to tens of thousands of years. The outer layers expand and contract rhythmically, each cycle expelling more and more material. During the AGB phase, something distinctive happens that separates it from the first red giant phase: thermal pulses. The helium-burning shell surrounding the carbon-oxygen core doesn't burn at a steady rate. Instead, it accumulates helium ash from the hydrogen shell above it until the helium layer becomes thick enough to ignite, at which point it fires in a brief, violent pulse, releasing enormous energy, dredging material from the deep interior up toward the surface, and then dying back down until the helium layer accumulates again. These thermal pulses occur every 10,000 to 100,000 years. Each pulse is accompanied by a powerful wind of material ejected from the star's surface. And each pulse dredges carbon from the interior up toward the outer layers. The Sun, which is primarily composed of hydrogen at its surface today, will become increasingly carbon-enriched at its surface as the AGB progresses. By the end of the AGB phase, the Sun's surface chemistry will be dramatically different from today. The stellar wind during the AGB phase is far more powerful than anything the Sun produces today. Today, the Sun loses mass at a rate of about 1.4 times 10 to the minus 14 solar masses per year, a tiny trickle. During the AGB phase, the mass loss rate increases by factors of 1 billion or more. The Sun sheds mass at a rate of perhaps 10 to the minus 4 to 10 to the minus 5 solar masses per year during its most intense phases. This mass doesn't disappear. It forms a slowly expanding cloud of gas and dust around the star, enriched with carbon, oxygen, and other elements synthesized in the star's interior. This cloud, this envelope of expelled stellar material, is the raw material for what comes next. For the next generation of planets, for the next generation of chemistry, potentially for the next generation of life. Everything the Sun synthesizes in its death, every carbon atom, every oxygen atom, every trace element forged in the fires of stellar evolution is being returned to the universe, scattered into the interstellar medium where it will mix with hydrogen and other elements. Eventually, in hundreds of millions of years, that material will be incorporated into new molecular clouds. Those clouds will collapse. New stars will form. New planetary systems will form. And on some of those new planets, in perhaps 1 billion years after the sun's death, the atoms that were once inside this star might find themselves arranged into something extraordinary. The atoms in your body were made in stars. The carbon in your DNA, the oxygen in your lungs, the iron in your blood. All of it was synthesized in the cores and explosions of stars that lived and died before the sun was born. When the sun dies, it returns its material to the universe, and the universe uses it again. Death is not the end of the story. It's the middle. The AGB phase ends with one of the most dramatic transitions in stellar evolution. The mass loss rate during the AGB becomes so extreme, so much material expelled so quickly, that the outer layers of the star are entirely removed. One final, powerful superwind strips away the last of the red giant envelope, exposing what's underneath. What's underneath is extraordinary. The core of the sun, the dense, hot, compressed remnant of 10 billion years of nuclear burning, is exposed. This core is incredibly hot. As the outer layers are stripped away and the core is no longer insulated by the overlying stellar material, it radiates freely into space. Its temperature can reach 100,000 to 200,000 degrees Celsius. Far hotter than the current surface of the sun. Hotter, in fact, than most stellar surfaces in the galaxy. At those temperatures, the core radiates intensely in the ultraviolet and extreme ultraviolet. And that ultraviolet radiation hits the cloud of expelled material surrounding it, the remnant of the AGB mass loss, and ionizes it, strips the electrons from the atoms. The ionized gas glows. It emits light. Characteristic colors determined by the elements present and the temperature of the radiation illuminating them. This glowing cloud of ionized expelled material, lit by the ultraviolet blaze of the exposed stellar core, is called a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. When astronomers first observed them through small telescopes in the 18th and 19th centuries, their round, disc-like appearance reminded some observers of the visual appearance of the outer planets like Uranus and Neptune. The name stuck despite being inaccurate. Planetary nebulae are among the most beautiful objects in the universe. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, sometimes called the Eye of God, the Butterfly Nebula in Scorpius, with 2 lobes of glowing gas expanding from a dying star, the Cat's Eye Nebula with its complex concentric shells, the Blinking Planetary in Cygnus, hundreds of known planetary nebulae, each one unique, each one the expelled shell of a star that died the way our sun will die. The shapes of planetary nebulae are determined by how the mass was expelled during the AGB phase. If the mass loss was spherically symmetric, you get a roughly spherical or ring-shaped nebula. If there was a binary companion affecting the mass loss, if the dying star had another star nearby, you might get bipolar jets, producing the butterfly or hourglass shapes. If there were magnetic fields or differential rotation affecting the winds, you get pinwheels, spirals, concentric shells. The Sun, as a single star without a known stellar companion, would likely produce a roughly spherical planetary nebula, perhaps with some asymmetry due to rotation or magnetic effects. It would glow with characteristic colors: red from hydrogen emission, blue-green from doubly ionized oxygen, other colors from nitrogen, helium, sulfur, and other elements. When the Sun produces its planetary nebula, the solar system, whatever remains of it, will be immersed in this glowing cloud for perhaps 10,000 to 20,000 years. The surviving outer planets, Jupiter, Saturn, Uranus, Neptune, in their new expanded orbits, will be bathed in the material expelled from the star they've orbited for 10 billion years. The sky, if any were alive to see it, would glow. From other star systems, the solar planetary nebula would be visible. A glowing structure, perhaps a light year or more across, centered on a tiny hot point of light. Anyone with a telescope within a few thousand light years watching the Sun's death would see it. A sun-like star, brightening, expanding, reddening over millions of years, then shedding its outer layers in a beautiful expanding cloud. Another ordinary death. Another planetary nebula added to the galaxy's growing collection. The planetary nebula phase lasts only 10,000 to 20,000 years. Then the expelled material expands far enough that it becomes too thin to glow. It disperses into the interstellar medium, mixing with the gas and dust between the stars. The central remnant, the exposed core, continues to shine in the ultraviolet and slowly cool. The monument to the Sun's death fades. The solar system falls quiet. What remains is the white dwarf. The white dwarf is the endpoint of the Sun's life. Not a supernova, only stars significantly more massive than the Sun end in that dramatic explosion. Not a neutron star or black hole. Again, those require much more massive progenitors. The Sun ends as a white dwarf, a dense, hot, slowly cooling remnant. The white dwarf will contain approximately half the Sun's original mass, perhaps a bit more, depending on the total mass loss during the giant phases. That mass, currently spread across a sphere 1.4 million kilometers in diameter, will be compressed into a sphere roughly 13,000 kilometers in diameter. About the size of Earth, maybe slightly larger. The density is staggering. A cubic centimeter of white dwarf material, a volume the size of a sugar cube, would contain roughly 1 metric ton of matter on Earth. 1 cubic centimeter, 1 metric ton. You could not lift it. You could not even budge it with any force available to human technology. It would simply sit there, impossibly dense, held up from further collapse not by nuclear reactions, but by electron degeneracy pressure. The quantum mechanical resistance of electrons to being packed more tightly together. The white dwarf will initially be extraordinarily hot. When first exposed as the AGB phase ends and the outer layers are stripped away, the core temperature may exceed 100,000 degrees Celsius. It will glow blue-white intensely, packing enormous amounts of luminosity into its tiny surface area. But it is not generating energy. There is no fusion happening inside a white dwarf. No hydrogen burning, no helium burning, no carbon burning. The carbon-oxygen core never gets hot enough for carbon to ignite in a sun-like star's white dwarf. The white dwarf is living off its thermal reservoir. It is simply radiating stored heat, like a brick taken from a fire and cooling in a cold room. The energy was stored during 10 billion years of nuclear burning, and now it leaks away into space. the rate of cooling slows as the white dwarf cools down. A very hot white dwarf radiates intensely and cools relatively quickly. A cooler white dwarf radiates less and cools more slowly. The cooling curve is not linear. The cooling decelerates over time. In roughly 1 billion years after the Sun becomes a white dwarf, its surface temperature will have dropped to perhaps 10,000 to 15,000 degrees Celsius. Still intensely hot by human standards, but dim compared to its initial state. It would appear white hot. Its luminosity would be perhaps 1% of the current Sun's luminosity. Nearby planets, Jupiter in its expanded orbit, would receive negligible warmth. The outer solar system would be far colder than it is today, despite the temporary warmth of the red giant phase. In roughly 5 billion years after becoming a white dwarf, roughly 10 billion years from now, the surface temperature will have dropped to perhaps 5,000 to 8,000 degrees Celsius. It would glow orange-yellow. Its luminosity would be a tiny fraction of the current Sun's. The solar system would be dark and cold. No atmosphere anywhere. No liquid water anywhere. Just the remnants of worlds in expanded orbits around a dim, cooling ember. After 10 billion years of cooling, it would be perhaps 3,000 to 4,000 degrees Celsius. Glowing a dull red, invisible to the naked eye from any reasonable distance. A cold stellar corpse in the galaxy. After 100 billion years, 10 times the current age of the universe, it would be perhaps 2,000 degrees Celsius. Barely glowing. A dark ember. After 1 trillion years, 100 times the current age of the universe, it would be below 1,000 degrees Celsius. Still faintly warm, but radiating almost no light. And eventually, after a time period that exceeds the current age of the universe by many orders of magnitude, perhaps in the range of 10 to the 15th years, the white dwarf will cool below 100 degrees Celsius. It will become cold. It will become dark. It will stop emitting any detectable radiation. It will become what physicists call a black dwarf. No black dwarfs exist yet. The universe is not old enough. Every white dwarf ever formed from every star that has ever lived and died is still warm, still cooling, still radiating. The universe is in its youth, and the first black dwarfs lie unimaginably far in the future. But they will come, eventually. In a universe that has grown cold and dark, scattered throughout it will be the black dwarfs, inert, dense, cold remnants of stars that once burned. Ghosts of suns, silent markers of what once was. The sun will become one of them. In the unimaginably distant future, after billions of years of warmth, billions of years of cooling, the sun will join the darkness. After everything, after the expansion and shedding and flash and nebula and cooling, what remains? The outer solar system survives, in a form. Jupiter, Saturn, Uranus, and Neptune will drift to larger orbits during the sun's mass-shedding phases, but they will remain gravitationally bound to the white dwarf. They'll continue orbiting, silent, frozen, no warmth reaching them, no light sufficient for any chemistry we know of. Jupiter's atmosphere, which is already mostly hydrogen and helium, similar to the composition of the sun itself, will simply freeze further. Its cloud systems, its bands, its great red spot, all of the atmospheric dynamics we observe today are driven by the combination of internal heat from formation and solar heating. With both sources reduced to negligible levels, Jupiter's atmosphere will settle into a far simpler, more uniform structure. It will cool dramatically. Over billions of years, it will become one of the coldest places in what was once the solar system. Saturn's rings, already destined to disappear through the inspiral of ring particles over the next few 100 million years, will be long gone. Saturn, without its rings, is a smaller, less dramatic world. Just another gas giant orbiting in the dark. The Kuiper Belt objects, Pluto and its siblings, the many small icy worlds beyond Neptune, will also drift outward. They'll remain in the solar system, cold and dark, probably forever unchanged from their current state. In many ways, the Kuiper Belt objects are the most stable things in the solar system. They've been frozen since the solar system formed. They'll remain frozen through the sun's death. They'll continue orbiting the white dwarf for as long as the solar system persists. The asteroid belt, sitting between Mars and Jupiter, will have been dramatically disrupted during the red giant phase. The expansion of the sun's outer layers, the intense solar wind, and the gravitational perturbations from the changing orbital dynamics of the planets will scatter asteroids across the inner solar system and beyond. Some will be accreted onto the white dwarf. Some will be ejected entirely from the solar system. Some will be drawn into eccentric orbits that bring them through the outer solar system. The orderly belt we see today will be a chaotic, dispersed population by the time the white dwarf forms. Some asteroids will actually fall onto the white dwarf itself over the billions of years following its formation. We know this happens because astronomers have observed white dwarfs with metal-polluted atmospheres, heavy elements like calcium, iron, silicon, magnesium, detectable in the white dwarf spectrum. The only way to get those heavy elements into the atmosphere of a white dwarf is for rocky material to fall onto it. We are watching, in other solar systems, the death of planetary systems. Rocky material that was once asteroids or planetary fragments or moon fragments falling onto the dense remnant of the star that once warmed them. The solar system's white dwarf will be polluted by its own asteroid belt. Over millions of years after the AGB phase, rocky material will rain down onto the white dwarf. The calcium and iron and silicon that were once in asteroids, in Mars, in the inner planets, vaporized during the giant phases, will gradually be absorbed into the white dwarf. The solar system eating itself. And what about the Oort cloud, the distant spherical shell of comets that surrounds the solar system at distances of up to 100,000 astronomical units? As the sun loses mass during the giant phases, the objects in the Oort cloud, already barely gravitationally bound, will become unbound. They'll drift away. They'll become interstellar objects, pieces of our solar system scattered across the galaxy. We may already be seeing the products of other solar systems' deaths. Interstellar objects have been detected passing through our solar system. Oumuamua in 2017, Borisov in 2019. These objects originated in other solar systems and are now traveling through ours. As the sun dies and the Oort cloud disperses, fragments of our solar system will similarly travel through other star systems across the galaxy. Pieces of what was once our solar system, scattered by the death of our sun, moving through the galaxy forever. The solar system, slowly, over billions of years, dissolves. We've been talking about the sun's life and death in isolation. But the sun doesn't exist in isolation. It orbits the Milky Way galaxy. And in the time remaining in the sun's life, the galaxy itself will change. The sun currently orbits the galactic center at a distance of about 26,000 light-years, completing one orbit in approximately 225 to 250 million years. In the 5 billion years remaining in the sun's main sequence life, the sun will complete approximately 20 more orbits of the galaxy, 20 more loops around the Milky Way, each one taking longer than the entire history of complex life on Earth. But here is something else happening on a similar timescale. The Andromeda Galaxy, our nearest large galactic neighbor, approximately 2.5 million light-years away, is approaching us. It is approaching at about 110 kilometers per second, and it is on a collision course with the Milky Way. In approximately 4.5 billion years, just before the sun leaves the main sequence, the Andromeda Galaxy will collide with the Milky Way. This will not be a collision in the conventional sense. Galaxies are mostly empty space. The stars in Andromeda will not crash into the stars in the Milky Way. The probability of any two individual stars colliding during the merger is vanishingly small. But the gravitational interaction between the two galaxies will be dramatic. Stars will be flung into new orbits. Tidal forces will distort the shapes of both galaxies. Spectacular tidal tails, streams of stars thrown outward by the gravitational interaction, will extend across hundreds of thousands of light-years. The merger will trigger intense episodes of star formation as gas clouds in both galaxies are compressed by the interaction and collapse into new stars. New nebulae will form. New star clusters will ignite. The solar system during this merger will likely be thrown into a significantly different orbit. It might end up much farther from the galactic center than it is today, or much closer. The orbital dynamics of a galactic merger are chaotic and difficult to predict precisely. But the solar system will survive. Individual stars almost never collide. The solar system will simply find itself in a different place within the merged galaxy, which astronomers have nicknamed Milkomeda. By the time the sun becomes a red giant, approximately 5 billion years from now, the Milky Way-Andromeda merger will be largely complete. The night sky. If any night sky existed anywhere in the solar system, which it won't, because life on Earth will have ended billions of years before this, would look utterly different. Instead of the familiar band of the Milky Way, there would be a large, irregularly shaped, elliptical galaxy filling much of the sky. The legacy of the merger. A new cosmic structure containing the stars of two previously separate galaxies, now intermingled. The sun's death will occur inside this merged galaxy. The planetary nebula will glow briefly within a galaxy that no longer looks like the one we know today. We've talked about what happens to the sun, what happens to Earth, what happens to the outer solar system, what happens to the galaxy. But there is one question we haven't addressed directly, and it's the most important one. What happens to us? Not to the physical matter of humanity, not to the atoms, but to the project of intelligence, to the continuity of whatever we become, to the possibility that something descended from this moment, this curiosity, this tendency to look up, survives. We have, as we've established, a approximately 1 billion years before Earth becomes uninhabitable to complex life. That is an almost incomprehensible amount of time. Modern Homo sapiens has existed for roughly 300,000 years. If we were to persist for 1 billion more years, and that's the minimum timeline before Earth becomes truly hostile, we would exist for more than 3,000 times as long as we already have. In 300,000 years, we went from stone tools to splitting the atom, from caves to cities, from running on savanna to landing on the moon. We went from no writing to the sum of all human knowledge stored in devices that fit in a pocket. We developed antibiotics, vaccines, gene therapy. We built telescopes that see the light from the Big Bang. We developed theories of space-time, quantum mechanics, the structure of the atom, the code of life itself. And we did all of that in 300,000 years, a blink. In 1 billion years, assuming technology continues to advance even at a fraction of its historical pace, what becomes possible is literally unimaginable. We cannot think about it the way we think about next year or next century. The distance between now and 1 billion years from now is greater than the distance between a bacterium and a human being. It's greater than the distance between the first eukaryotic cell and modern civilization. Anything could happen in that time. Everything will happen in that time. What we know, with physics-backed confidence, is that Earth becomes uninhabitable within that window. And what that means for our survival as a civilization is clear. We either become capable of living somewhere other than Earth, or we end. This is not pessimism. It is clarity. We already live in a solar system with many other worlds. Mars is the obvious near-term candidate, a world where humans could survive with effort, with technology, with the terraforming ambitions that some of our best scientists and engineers are already planning. The outer moons offer long-term possibilities. Space habitats, artificial constructed environments, could house enormous human populations entirely independent of any planetary surface. Freeman Dyson imagined megastructures that could support civilizations of staggering size using the full energy output of the sun. But the ultimate necessity is clearer still. We must eventually become an interstellar species. Not because we want to explore, though. Exploration is part of who we are. Not because Mars will become insufficient, though eventually it will. But because the sun itself is the threat. Every world in this solar system, every habitat, every structure, everything in the solar system depends on the sun. When the sun dies, the solar system becomes uninhabitable. Everything here ends. The only long-term survival for any intelligence originating in this solar system is to leave it. That departure need not happen in a rush. We have hundreds of millions of years before the situation becomes urgent. But the direction is clear. The destination is other stars, other solar systems, other suns. And here is the extraordinary thing. We are right now in the first moments of a species capable of considering this. We understand stellar evolution. We understand how stars die. We can calculate the timeline. We know we need to leave. And we are beginning, just barely beginning, to develop the technologies that make interstellar travel at least conceivable. Breakthrough Starshot is attempting to design laser-propelled probes capable of reaching Alpha Centauri. SpaceX is developing fully reusable launch vehicles that dramatically reduce the cost of reaching orbit. Various programs are working on nuclear propulsion systems that could make interplanetary travel faster and more practical. Researchers are studying the biology of long-duration spaceflight, the psychology of isolation, the closed-loop life support systems needed for decades-long journeys. We are in the earliest, most primitive stages of becoming a spacefaring species. We are at the moment equivalent to the first fish struggling onto land, barely beginning to access an environment that will eventually be entirely ours if we survive long enough to adapt to it. The fish that crawled out of the sea 375 million years ago did not know it was doing something historic. It did not know that its descendants would walk upright on dry land, would look up at the stars, would eventually leave the planet entirely. It simply followed wherever survival led. We know where survival leads: upward, outward, to other stars, before ours dies. Every star in the galaxy that has ever had a mass close to the sun's has died the same way. Main sequence burning, subgiant expansion, red giant, helium flash, asymptotic giant branch, planetary nebula, white dwarf, cooling to darkness. There are estimated to be roughly 10 billion white dwarfs in the Milky Way. 10 billion stellar remnants, each one the ghost of a sun that lived and died. Some of them older than our sun. Some of them that formed 10 billion years ago when the galaxy was young and the first generation of sun-like stars completed their lives. Those ancient white dwarfs have been cooling for 10 billion years. They are dim and dark, difficult to detect. The oldest white dwarfs in the galaxy are approaching temperatures where they can barely be detected at all. They are becoming the first black dwarfs. Not yet, because the universe is not quite old enough, but approaching it. And around each of those white dwarfs, orbiting in darkness, cold and silent, are the remnants of their solar systems. Other Jupiters, other outer planets, scattered and frozen. The relics of worlds that might once have had oceans and atmospheres and life. We cannot know. We don't have the technology to study the planetary systems around distant white dwarfs with the resolution needed to detect Earth-like planets. But we know that planetary systems are common around sun-like stars. Kepler and other planet-finding missions have established that most sun-like stars have planets. Most sun-like stars appear to have rocky, Earth-sized planets in or near the habitable zone. And all of those sun-like stars will eventually die the same way ours will. Which means that the death we've been describing tonight, the brightening, the ocean's evaporation, the expansion, the destruction of inner worlds, the brief warming of the outer solar system, the planetary nebula, the white dwarf, is not a unique catastrophe. It is the universal fate of rocky planets around sun-like stars. It has happened billions of times before in the history of this galaxy. It will happen billions of times more as the remaining sun-like stars age and die. The question of whether life exists elsewhere in the galaxy is directly connected to this. If life commonly arises around sun-like stars, then life commonly faces this same sequence of events. Life gets perhaps 1 billion years of stable main sequence conditions, maybe more, depending on the star's exact mass. Then the brightening begins. Then the oceans evaporate. Then the inner worlds are destroyed. If life exists elsewhere and follows a similar trajectory to life on Earth, slow to start, billions of years of single-celled organisms, then a relatively recent emergence of complex life and intelligence, then any given civilization is probably at some point in this timeline, either before the ocean evaporation crisis or after it. And the ones that survive past the ocean evaporation crisis are the ones that left, the ones that became interstellar before their sun forced the issue. This is the galactic filter in some ways. Not the extinction of life. Life is resilient and might persist in subsurface oceans or engineered environments, even as the surface becomes uninhabitable. But the extinction of civilization, of technology, of the capacity for interstellar travel. Any civilization that doesn't develop interstellar capability before its sun's brightening becomes critical will be trapped. It will decline with its planet's habitability. It will lose the energy, the resources, the stability needed to maintain technological civilization. It will end. The great silence of the universe, the apparent absence of detectable intelligent civilizations despite the enormous number of potentially habitable planets, might be partly explained by this. Many civilizations might arise, develop briefly, and then be extinguished not by war or ecological collapse, but simply by the ordinary aging of their star. They had a window. They didn't make it through. We have a window. About 1 billion years. The question is whether we make it through. Let's slow down and sit with something before we finish. Because we've been talking about the sun's death, its timeline, its consequences, its implications. And in doing so, it's possible to lose sight of what the sun actually is right now and what it gives. The sun is not a threat. Not yet. Not for hundreds of millions of years. The sun right now is the most generous thing in the solar system. An engine that has been running for 4.6 billion years, converting 600 million tons of hydrogen into helium every second, radiating the energy of that conversion in all directions. With a tiny fraction of it, an infinitesimal slice of its total output, falling on this small, rocky planet and driving every process of life. Every calorie of energy in every meal you've ever eaten traces back to the sun. The plants absorbed sunlight through photosynthesis. The animals that ate the plants absorbed that energy. The animals that ate those animals absorbed it again. The oil and gas we burn, the coal, is fossilized sunlight. Millions of years of plant matter that absorbed the sun's energy died, was buried, was compressed, and was preserved. When we burn it, we release sunlight from the Carboniferous period. The wind is solar energy. Temperature differences created by differential solar heating of Earth's surface drive atmospheric circulation. The waves on the ocean are partly driven by those winds. The water cycle, evaporation, clouds, rain, rivers, is driven by solar energy. Weather is solar energy. The currents in the ocean are partly driven by solar energy. The biosphere in its entirety, every living thing in every ocean and forest and desert and soil, is running on sunlight. We are sunlight. We are the sun's energy organized into complexity. Every thought you've ever had was powered by chemical reactions, ultimately tracing back to photons from the sun absorbed by plants. Every movement, every breath, every heartbeat. The sun is not external to us. It is inside us. It has always been inside us. And it has been doing this for 4.6 billion years without asking anything in return. The sun has been burning since before multicellular life existed, It warmed the oceans where the first complex cells evolved. It provided the energy for the first photosynthetic organisms to arise and begin filling the atmosphere with oxygen, transforming this planet from a world where complex life was impossible to one where it was inevitable. It lit the first forests of the Carboniferous period. It warmed the backs of the first dinosaurs. It has shone on every single day of human existence, from the first Homo sapiens walking the African savanna to this exact moment. And it will continue for another 5 billion years. That's not nothing. That's an astonishing gift. We live in the middle of our star's life, not at the beginning, when the solar system was chaotic and violent and inhospitable. Not at the end, when the heat will destroy everything we know. Exactly in the middle. The period of maximum stability. The period when the sun is old enough that its early energetic outbursts have settled, but young enough that its brightening hasn't yet destabilized the climate. The Goldilocks period of a star's life. We are extraordinarily lucky to be here now, in this solar system, at this time, with this sun. Let me give you the full timeline of the sun's remaining life, all of it in order, so you can hold the whole arc in your mind. Right now, the sun is 4.6 billion years old. Hydrogen fusion continues in the core. The sun is slightly brighter than when Earth formed. Life continues on Earth, for now, approximately 500 million to 800 million years from now. Conditions on Earth's surface become too hot for complex multicellular life. The CO2 level drops too low for most plant photosynthesis. Temperatures rise past the tolerance of complex ecosystems. Earth's biosphere collapses to microbial life in extreme environments. Approximately 1 billion to 1.5 billion years from now, the runaway greenhouse effect takes hold. Earth's oceans begin evaporating. The hydrogen is lost to space. Earth becomes a hot, waterless world. Approximately 1 to 2 billion years from now, Earth's surface resembles Venus today. Hot, acidic atmosphere, crushing carbon dioxide pressure, temperatures exceeding 400 degrees Celsius. No liquid water anywhere. Earth is effectively dead. Approximately 5 billion years from now, core hydrogen fusion in the sun ceases. The helium core begins contracting. Shell hydrogen fusion ignites. The sun begins expanding. The subgiant phase begins. Approximately 5.4 billion years from now. The sun is now significantly larger and more luminous. The habitable zone has moved outward past Mars. Whatever orbits there are baked, the expansion continues. Approximately 7 to 8 billion years from now, the sun reaches its maximum red giant size. Its radius has expanded to approximately 100 to 200 times its current size. Mercury and Venus are long gone. Earth is engulfed or barely escapes. But either way, the surface is vaporized rock. The outer solar system, for the first time, receives significant warmth. The helium flash occurs, restructuring the core and briefly contracting the outer layers. The sun enters the horizontal branch, a period of stable helium core fusion lasting approximately 100 million years. Approximately 8 to 8.5 billion years from now, helium core fusion ends. The asymptotic giant branch phase begins. The sun expands again, even more dramatically. Powerful thermal pulses, intense stellar winds. The sun begins shedding its outer layers. Approximately 8.5 to 9 billion years from now, the AGB phase ends. The last outer layers are expelled. the glowing planetary nebula forms and slowly expands. The hot core, the future white dwarf, is exposed. Approximately 9 billion years from now, the planetary nebula has dispersed. The white dwarf is alone. The solar system is dark, cold, and silent. The outer planets orbit in expanded orbits around the cooling remnant. The Milky Way-Andromeda merger is complete. 10 billion years from now, the white dwarf has cooled significantly, still warm by stellar standards, but dim. The solar system is thoroughly dark. Tens of billions of years from now, the white dwarf continues cooling. The solar system is thoroughly cold. The outer planets continue orbiting in silence. Trillions of years from now, the white dwarf is approaching black dwarf temperatures. The solar system is almost completely dark. The wider universe is also becoming dark as other stars complete their lives. Eventually, beyond any timescale we can meaningfully imagine, the white dwarf becomes a black dwarf. The sun, which once warmed a living world, falls silent. The final temperature difference between the remnant and the surrounding space approaches zero. The sun's story ends. There's a deep truth underneath everything we've talked about tonight, and I want to name it clearly before we close. The death of the sun is not a special event. It is not a catastrophe in the cosmic sense. It is ordinary. It is expected. It is the same thing that happens to every star of roughly this mass, in every galaxy, throughout the universe. It has happened billions of times before and will happen billions of times more. What makes it feel special, what makes it feel like a catastrophe, is that we are here, on this planet, warmed by this specific star. We have built our existence, our biology, our civilization, our entire concept of home around this one particular sun. And so its death is, to us, the end of everything we know. But the universe does not notice. The universe has billions of suns, and billions of those suns have died, and the universe continues. The material that made those suns, carbon, oxygen, nitrogen, iron, is returned to the interstellar medium, mixed with hydrogen clouds, incorporated into new stellar nurseries, assembled into new stars and new planets, and possibly new life. Nothing is wasted. Nothing is lost, only transformed. The carbon in your body was forged in a star that died before the sun was born. The oxygen you breathe was created in fusion reactions in stellar cores billions of years ago. The iron in your blood was synthesized in a supernova that scattered its elements across the galaxy. You are made of dead stars. You are the universe organizing itself into something that can wonder about dead stars. And when the sun dies, when the outer layers are shed and the planetary nebula glows and disperses, the atoms that were once the sun will join the interstellar medium. They'll mix with hydrogen clouds. Gravity will compress them, eventually, somewhere, into new stars. Some of those atoms will end up in planets around those new stars. Some might end up in environments where chemistry becomes biology. Some might end up in living things that look up at their own star and wonder. The atoms of the sun will outlive the sun. The atoms of the earth will outlive the earth. And the atoms of you, every atom in your body, will outlive you, and your civilization, and your planet, and your star. They will persist until the universe itself is too cold and dark for matter to do anything interesting. That's a long time. A very long time. In a universe that vast, in a time frame that long, Meaning doesn't come from permanence. Nothing is permanent. Not stars, not planets, not species, not civilizations. Meaning comes from what we do with the time we have, from what we build and create and discover and love and pass on. The sun will die. Earth will be destroyed. Complex life here has perhaps 600 million years remaining. We have been civilized for 10,000 years. We have been a technological species for 300. The gap between what we are and what we need to become, a species capable of leaving this solar system before it becomes uninhabitable, is vast, but not unbridgeable. The question is not whether the sun dies. It does. The question is not whether Earth survives. It doesn't. The question is whether we do. Whether something descended from this moment, this curiosity, this capacity to understand, this habit of looking up, persists long enough, grows far enough, spreads widely enough, to be somewhere else when the end comes here. I believe we can. Not because I'm optimistic by temperament, but because I know what we've already accomplished in 300,000 years. And because I know we have approximately 500 million years before things get truly urgent. That is time enough if we use it well. Tonight, before you sleep, go outside, if you can, or stand at a window. Look up. You cannot see the sun at night, of course. It is on the other side of the world, warming other people, illuminating other oceans. But you can see its legacy in the darkness. The stars around us, the points of light scattered across the sky, are other suns, many of them older than ours, many of them younger, each one burning hydrogen into helium, each one on its own timeline toward its own version of what we've described tonight. The Milky Way stretched across the sky is a population of stars in various stages of their lives. Young blue stars burning intensely and briefly. Middle-aged yellow stars like our own. Old red giants in their final expansions. White dwarfs cooling in silence. Nebulae formed from the deaths of stars, seeds of new stellar generations. It is all happening right now, in this moment. Every stage we've described tonight is occurring somewhere in the galaxy. Some star somewhere is having its helium flash. Some star is entering its red giant phase. Some star is shedding its outer layers. Some white dwarf is cooling that was formed before our solar system existed. And somewhere around some star in some galaxy, life is watching its sun die. We are watching our sun live. Alive for 4.6 billion years. Midway through. Still burning steadily. Still providing the energy that sustains every living thing on this planet. Still warming the faces of people who look up and wonder. The sun is not eternal. We know that now. We know how it ends, in what sequence, on what timeline. We know what it means for Earth, for life, for us. We know the urgency it implies for what we must eventually become. And knowing that makes tonight's sky different. Not darker, not more frightening, more honest, more real. The sun that rises tomorrow morning is not just a source of light and warmth. It is a nuclear furnace 4.6 billion years into its life. It is halfway through. It has given us everything we have and everything we are. And in the fullness of geological and astronomical time, it will take it all back. That is the deal. That has always been the deal. We live on borrowed warmth from a temporary star. What we do with that loan is up to us. Thank you for spending this time with me tonight. exploring one of the deepest stories the universe has to tell. If this changed how you look at the sky, if it made the sun feel more real and more present, please take a moment to like the video and subscribe to the channel. These deep explorations take real time and care, and your support is what makes them possible. The sun will rise tomorrow. It will rise for billions more tomorrows after that. Feel it on your face. Understand what it is. Know what it will become. And go forward with clarity about the extraordinary, temporary, irreplaceable gift of a living world orbiting a living star. Sleep well. The sun will be there in the morning. For now.